Hi everybody, and welcome to section 15.6 on triple integrals. So, last few sections we talked about different ways to find double integrals, and we said the double integrals found the volume of some shape of some region. So what about triple integrals? Well, we can look at triple integrals visually by dividing some surface up into several boxes. These boxes will have a width of delta y, a length of delta x, and a height of delta z. So if we're looking to find the volume of this rectangular prism here, we can do the same thing, divide this into a number of boxes, sum up all the boxes, great, we find the volume. If this is a more abstract surface, naturally, the larger the number of boxes, the more accurate this volume is going to be. Now, we could absolutely do this with double integrals. Because this is just a box, we could define z as a function of x and y. Let's say, well, this box is 6 units tall, so if we just defined z as 6, in this case we could find the volume either way, with a double or a triple integral. So this is true when we just have a constant inside of this integral. When we have an actual function inside of this triple integral, then it gets just a little bit more abstract. So then we're talking about actually finding the volume of a four-dimensional region, which we cannot picture. But in this case, what we can picture is our integration region, which now is a three-dimensional region. So, past few sections with double integrals, our integration region was in 2 dimensions, so we found the volume. Now we're going to find the 4-dimensional volume, if you want to call it that, and our integration region is in 3 dimensions. So in this way, we actually can switch up our order. There were 2 different orders in which we could write that 2-dimensional integral, but now we have 6, because we can write dx, dy, dz, dx, dz, dy, dy, dz, dx, and so on. We can switch up this order. And this is going to be important because we can't directly integrate every expression with respect to each order. So this is going to help us to integrate more easily if we can switch up the order. So let's start with a more basic example. We want to evaluate the triple integral of x, y, z squared dv, where b is the rectangular box given by these restrictions. So here our integration region is a rectangular box. If I were to sketch that integration region, that would be in 3 dimensions. Okay, x would go from 0 to 1. Y is going to go from -1 to 2, from -1 to 2, and z is going to go from 0 to 3. So I can sketch it. It's going to look something like this. So this is my integration region. We can just immediately set up this double integral because we know our integration region is going to form the bounds on this in this integration. Now the question is, does it matter what order we write these in? Should our bounds be dx, dy, dz, dc, dy, dx, and so on? Well, in this case we can see that it doesn't really matter. No matter how we write this, we've got an x, y, and a z inside of this integral, so as our integrand. And when we integrate with respect to x, y, and z are treated as constants. When we integrate with respect to y, x and z are treated as constants. With respect to z, x, and y are treated as constants. So let's just set this up, giving ourselves plenty of room here, starting with dx. meaning that our inner bounds are going from 0 to 1. dy, meaning our middle bounds are going from -1 to 2. And dz, meaning our outer bounds are going from 0 to 3. So we want to integrate this over this rectangular prism of a region with x, y, and z boundaries. All right, now we have this one theorem that says that if we have something written in the form of f of x times g of y dx dy, then we can break this up into the integral of f of x dx times the integral of gy dy. Same thing applies to 3 dimensions as well. So in 3 dimensions, we can just break this up because we can write this as a function of x times a function of y times a function of z. This is just going to save us a little bit of time in the long run. So we can break this up into our integral from 0 to 3. Remembering that these are our z bounds, so this is going to be z squared dz times the integral from -1 to 2. These are our y bounds, and that function is just going to be y dy times the integral from 0 to 1. These are our x bounds, and so we've got x dx. So evaluating these, starting with the left, the antiderivative of z squared is 1/3 z cubed. We're going from 0 to 3. Plugging in 3, well, 3 cubed is 27. 27 divided by 3 is 9. When we plug in a 0, we just get 0, so this is just going to be 9. Our second integral, when we take the antiderivative of y, that will give us 1/2 y squared, bringing that from -1 to 2. So plugging this 2 in, we get 1/2 of 4, which is 2. Plugging in -1, we get -1 squared, which is a +1, times 1/2. And 2 minus 1/2 is the same as 4/2 minus 1/2, which is 3/2. Finally, antiderivative of x with respect to x is 1/2 x squared. Taking that from 0 to 1, this is just going to give us 1/2 times 1 minus 0, which is 1/2. Finally, we're multiplying these together, and 9 times 3/2 times 1/2 is going to be 27 over 4. And because, this is really going to be a 4-dimensional value. If we're talking about volume, it's going to kind of be volume in 4 dimensions. However, we're not really going to ask you for units unless we're talking about some application problem, which doesn't come up too much in this class. So we're going to leave this as 27 over 4, understanding that this is a bit of an abstract solution here. And that's all there is to it. Technique is very much the same as with 2 dimensions. These rules that we can apply, these shortcuts, are the same with 2 dimensions. We can move to polar coordinates just like we did in 2 dimensions. The only thing that's a little bit more complicated is finding our bounds, which now have 3 dimensions to them. So with that, let's look at another example with bounds that are not necessarily constants. Example 2, we want to evaluate this triple integral of y dv, where e is equal to the region in x, y, and z, and this is just that domain notation that we saw earlier in this unit, in this class rather, where x goes from 0 to 3, y from 0 to x, and z from x minus y to x plus y. And in this case, you can see that y is a function of x. So y is a function of x. we can see based on this domain, this region of integration, that z is a function, and I'll just call that a different function g, of x and y. And in this case, the order of integration does matter. Because if I were to have my final integral be in terms of z, then I would be left with variables of x and y. And so there's only one way I can write this triple integral. So let's write this triple integral. This is going to be y. And now, I know my x bounds must be on the outside because these are in terms of constants. So x must go from 0 to 3. Y is a function of x. So that's going to be my middle bounds. Y goes from 0 to x. And z is a function of x and y, so it must be in the middle. So z is going to go from x minus y to x plus y. All right, so this gives me dz, dy, dx. So now I can start to evaluate. Now, rather than rewrite all of these bounds every single time, I'm just going to focus on the innermost integral at a time. So looking at taking the integral of y with respect to z. Well, with respect to z, y is just a constant, so this is really going to turn into yz, as z goes from x minus y to x plus y. So plugging this in for z, this is going to look like y times x plus y minus y times x minus y, which is xy minus xy, so those cancel out, plus y squared plus y squared, so we are just left with 2y squared. So this is our innermost integrand, so this is going to turn into the double integral from 0 to 3 and from 0 to x of 2y squared. We've taken this integral with respect to z, so we're just left with dy dx. So we're just working our way down. Now taking this innermost integral, with respect to y, when we take the integral of 2y squared, we are left with 2y cubed divided by 3. So that's going to look like 2/3 y cubed, taking that from 0 to x. This means we will be left with 2/3 x cubed minus 2/3 times 0. So finally, our outermost integral from 0 to 3 is going to be of 2/3 x cubed dx. And we can always, at any stage in this, we could have pulled this 2 out in front of both integrals. We could pull this 2/3 out. We could always pull a constant out of all of these integrals. So that rule remains. So taking this integral, well, the antiderivative of 2/3 x cubed is going to be 2/3 x to the 4th power divided by 4. So that's going to look like 1/6 x to the 4th power from 0 to 3. 3 to the 4th power is 81, so this is going to look like 81 over 6 minus 0. And let's see, 81 is 27 times 3, so we can also write this as 27 over 2. So this is that integration. And again, our units are going to be a little bit abstract. Instead of writing units to the 4th power, we can just leave this as a constant. So now let's talk about categorizing the different types of regions. In 2 dimensions, if we remember, we had a type 1 solid region and a type 2 solid region. Now again, it's not that important that you remember which type is which. But just the distinction of how we can break these up in different ways. Now we're saying a type 1 solid region lies between 2 continuous functions of x and y. In other words, our z bounds are a function of x and y. So z is a function of x and y. Now within this type 1 solid region, we have two different situations here. We can either have our y bounds be a function of x, or our x bounds be a function of y. So this type 1 solid region means that our integral is automatically going to be written as dz times dA, where dA is either dx dy or dy dx. So in this case, where y is a function of x, we would be writing this triple integral as dz, d, and now y is a function of x, dx. In this case, because x is a function of y, we would write that triple integral dz, dx, dy, just keeping the constants on the outside so that we're left with just a constant and not variables. If we look at the projections, so this would be the projection of this surface, because this is a type 1 region, onto the yz plane. Then we could write this again where y is a function of x. So again, if I see a vertical arrow here, I know this must be y equals something. What that tells me is that y is going to go from this function. So whatever this function is, it looks like the square root of x, but we're not sure. So y is going to go from this function of x to 1. X will then go from 0 to 1. In this other case, looking at this projection onto the xy plane, we can draw this horizontal arrow, which means that our x is going to be a function of y. And so our x can be written as 0 to, in this case, x, that function of y. So we can write that g of y. And then y just goes from 0 to 1. So we have the two different types of type 1 solid regions. So there are 6 different types of solid regions we can find. So let's do this next example. Example 3. Evaluate this triple integral of E dv, where E is a solid tetrahedron bounded by the 4 planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. So let's start by sketching this out. So x equals 0, y equals 0, z equals 0. Well, all this means is that our region is in the first octant. Now for x plus y plus z equals 1, well, we can plot these intercepts. So our x-intercept occurs when y is 0 and z is 0. We know that's going to be 1. Likewise, because we have x plus y plus z equals 1, we know we have a y-intercept of 1 and a z-intercept of 1. So our tetrahedron is going to look something like this, with a z of 1, an x of 1, and a y of 1. Let's fix this line. Okay, and this is going to be our region. Now this is going to connect, it might be a little difficult to see, but it's going to connect to all of these planes. Tetrahedron is really a fancy word for triangular prism. So it's going to be this triangular prism. Now, let's call this a type 1 region. Type 1 means we have dz, dA. So that means z is a function of x and y. So if I look at this region and I say, okay, how can I categorize my height of this tetrahedron at any point? From the base of this thing, well, isn't z always 0 at the base of this? And then my height, what stops my height from increasing is this plane. So this plane is going to be my upper bound. So if z is a function of x and y, then I can say that z goes from 0 to this plane. I can write this plane z equals 1 minus x minus y. So my z goes from 0 to 1 minus x minus y. So these are my z bounds. Now to find my x and y bounds, I'm going to want to use the projections on the x and y plane. So on the xy plane, well, I know this is going to be in the first octant, so I'm just going to worry about my positive x and y axes. And now I can draw where this line is. I know this line intersects at y equals 1 and x equals 1. So this is my integration region. Okay. Now, I could draw a vertical or a horizontal arrow. It doesn't really matter which, because again, I'm going from one function to another. So let's start with horizontal. If I have a horizontal arrow, that means that my x bounds are going to be a function of y. So what that means is x is going to go from 0 to, now what's this line? Well, this line occurs when z equals 0, so x plus y equals 1. If I want to write x as a function of y, I can just move that y over and say that x is equal to 1 minus y. So my x is going to go from 0 to 1 minus y. If my x is a function of y, then for my y bounds, I'm just going to use those constants. So y just goes from 0 to 1. Finally, we have everything we need. We have our z bounds, we have our x bounds, and we have our y bounds. We also know the order that we need to write these in. We know we need to write these starting with our constants. So from 0 to 1, we can then write x as a function of y, so from 0 to 1 minus y. And then we can write z as our function of x and y, so 0 to 1 minus x minus y. We want to take this integral of z, and our order then would need to be dz, dx, dy. Now I just picked that this is going to be a type 1 region, and then that our x bounds are going to be in terms of y. But what if I wanted to go the other way? If I wanted y to be a function of x, my arrow would look like this. Y would be a function of x. Then my y bounds would go from 0 to, now I could also rewrite this equation as y equals 1 minus x. So my y would go from 0 to 1 minus x. Then my x would just go from 0 to 1. So I could also write this as the integral from 0 to 1, from 0 to 1 minus x. And then because these are both type 1 regions, my z-bounds are going to stay the same. So from 0 to 1 minus x minus y of z dz dy dx. So these are the two different types of type 1 regions. They're going to be exactly the same. Let me just actually move this over, and then we're just going to evaluate this first integral we found. So evaluating this, let's start with the z. The integral of z with respect to z is just 1/2 z squared. That's going from 0 to 1 minus x minus y. All right, so this is going to be 1/2 times 1 minus x minus y squared minus 0. So now we have this double integral from 0 to 1 and from 0 to 1 minus y of 1/2 times 1 minus x minus y squared dx dy. Now sure, I could expand out this trinomial. I like to avoid expanding out trinomials when I can, just because it's a little bit tedious. Because right here, can't I also just use u substitution? I mean, I could just call this, let's see, if we let u be 1 minus x minus y, then our du, remember that we're integrating it in terms of x, treating y as a constant, would just be -1 dx. So I can rewrite this inner integral as, let me pull the 1/2 out to the front, times the integral of u squared du, and I'll pull this negative out to the front as well. Well, this is going to give us -1/2 times 1/3 u cubed. Rewriting this back in terms of x, this gives us -1/6 times 1 minus x minus y cubed. And we're taking that from 0 to 1 minus y, which gives us -1/6 times 1 minus, remember that we're just substituting this in for all of our x's, so 1 minus y minus y, all of this cubed, minus the quantity 1 minus 0, so I'll just call that a 1 minus y cubed. So let's just finish this on a new slide. And simplifying this, we get, well, 1 minus 1 minus y minus y. That's just going to turn into a y minus y, so that's just 0. And so we are just going to be left with a -1 times 1/6 times a negative, so positive 1/6 times 1 minus y cubed. All right, and then our final integral was from 0 to 1 of, this is going to be, and let me pull this 1/6 out to the front, of 1 minus y cubed dy. Let's just double check that. Yep, so this outermost integral from 0 to 1 dy. All right, so for this one, we'll also need another u substitution, unless we feel like expanding this binomial out 3 times, which I do not. So let's call this u equals 1 minus y, meaning our du is -1 dy. So we can rewrite this as -1/6 times the integral of u cubed du, which turns into -1/6 times 1/4 u to the 4th power. And this gives us negative 1 over 24 times the quantity 1 minus y to the 4th power, taking that from 0 to 1, which is negative 1 over 24, times, well, 1 minus 1 is just 0. 1 minus 0 is 1 to the 4th power, which is 1. And so we're just left with a positive 1 over 24. We've successfully evaluated that integral. So now let's look at these type 2 and type 3 triple integrals. So for a type 2 solid region, a type 2 solid region occurs where D is the projection of E onto the YZ plane. In other words, X, in this case X, is a function of Y and Z. Now within that, because we know that this must be in the form of dx dA, we can now write this area as a type 1 region or a type 2 region. Remembering that in a type 1 region, when we're talking about this being a dx dy dz or dx dz dy, now we're looking at this region being the projection onto the zy plane. So this is the zy plane. And in a type 1 region, we can draw this vertical arrow and we can write these bounds as where z is a function of y. So where's z? And in this case, because this is 1, and let's see, this is also 1, so 1 and 1, we can write this as z equals y minus 1, just because we know that this is going to be z plus y equals 1. So we can write z as y minus 1. So this means that our bounds, in terms of z, well, z is going from 0 to y minus 1, and y is just going to be my constants from 0 to 1. As a type 2 region, I can draw this horizontal arrow, and because this is my z and y axis, because this arrow is parallel to my y-axis, my y bounds are going to be a function of of z. So my y bounds are going to go from 0 to, and I can write this as y equals z minus 1. So y goes from 0 to z minus 1. And z, I want to keep bringing back x, but z goes from 0 to 1. Now finally, a type 3 solid region occurs where y is a function of x and z. So we're looking at the xz plane to find our second two sets of bounds. A type 1 region on the z-x plane, remembering that this line is just going to be z plus x equals 1. We could draw a vertical arrow. This vertical arrow is parallel to the z-axis, so this is going to be z equals something. Rewriting this equation, we get z equals 1 minus x. So our z bounds are going to go from 0 to 1 minus x. Our x bounds are going from 0 to 1. Finally, a type 3 solid with a type 2 region means now we're breaking this projection up with a horizontal arrow because this is the z-x plane. This horizontal arrow is parallel to the x-axis, so we can rewrite this as x equals something. rewriting this equation, we can write this as x equals 1 minus z. And so our x bounds go from 0 to 1 minus z. And our y bounds, oh my goodness, our z bounds go from 0 to 1. And we have a little summary here of what happens. All right, so let's do this example, and we're going to set it up the 6 different ways using a type 1, type 2, and type 3 region. So with a type 1 region, we want to evaluate this. Now, this isn't pictured. This square root of x squared plus z squared is not pictured here. This is just the region of integration. We don't actually ever really need to picture this because this is just what we are integrating. We're only worried about the region of integration here. So let's just label this as our region of integration. Okay. And because we want to evaluate this as a type 1 means our bounds are going to look like dz dA, where dA is either dx dy or dy dx. So starting with z, I need to rewrite this as a function of x and y. So I'm starting with y equals x squared plus z squared. I want to rewrite this as a function of x and y. So isolating that z, I get that z is equal to, well, the square root plus or minus the square root of y minus x squared. So when I'm looking at this, as far as my z values go, I know my z is going to start down here and go up to the top. Because I have this plus or minus, I know that this is going to be minus root y minus x squared, and this is going to be positive square root of y minus x squared. So this is that positive, and this is that negative. So these are my z bounds. So z is going to go from negative root y minus x squared to positive root y minus x squared. All right, so I've got my dz. Now for my dy or dx, let's sketch the xy plane. So sketching this on the xy plane, what is this going to look like? Well, if I want to find the projection of this onto the xy plane, I can see based on this graph, this parabola is actually the largest at z equals 0. So if I'm picturing a view from above this shape here, I have a parabola opening toward the positive y-axis. And so I'm told that this is my paraboloid, y equals x squared plus z squared. Well, at z equals 0, this is going to be y equals x squared. So this is my y equals x squared. And the plane y equals 4. So in 2 dimensions, this is just going to be the line y equals 4. Meaning this is our integration region in 2 dimensions. So now if I want to call this a type 1, which is a little bit easier of an integration, right? Because then I wouldn't have to go from a negative, I wouldn't have to break this parabola up. This is already written as y equals something. Then I could break this up going from y well, where's my lower bound of this arrow? It's x squared. Y equals x squared. Where's my upper bound of this arrow? The upper bound of this region is just 4. And then my x, well, I need to find this intersection. So to find these intersections, let's set x squared equal to 4, which means that x is equal to plus or minus 2. So this is going to be negative 2, and this is positive 2. So my x is going from negative 2 to positive 2. All right, so we've got everything we need to set up this integral. So let's set up this triple integral. Our outermost bounds are going to be those constants, so from negative 2 to 2. Our second set of bounds is where y is a function of x, so from x squared to 4. And our third set of bounds is going to be our z bounds as a function of x and y, so from negative root y minus x squared to positive root y minus x squared. Inside we have the square root of x squared plus z squared. Now we have dz, dy, dx. Now looking at this, we want to first start by integrating this expression with respect to z. Now I have a z squared inside of a square root attached to an x squared. I can't use u substitution. I can't use integration by parts. What I would need to do was I would actually need to start with trig substitution. And this would be a very difficult thing to integrate. So very difficult to integrate. So we are starting off with a trig substitution of z equals x tangent theta. Then when we move along, we end up needing to use another integration by parts, and then a couple other trig identities just to evaluate that first integral, in case anyone is curious. So let's try setting this up as a type 2 integral. Remembering that a type 2 integral is an integral in the form of where we have this triple integral and it's something, and in this case that something is going to be x squared plus z squared dx dA. So x is a function of y and z. So looking at these x values here, my x going from a negative to a positive x value. If I can kind of picture this starting on the outer rim of this paraboloid here and moving in the positive z direction to somewhere along this outer edge. Now if I rewrite this in the form of x equals something, I can rewrite this as x equals, let's see, I'd have to bring this z squared to the other side, take the square root of everything, so plus or minus square root of y minus z squared. All right, well, because this is where, in this case, this axis, this is really where my negative x values are. So going from negative to positive, because if I'm looking at this z-axis, and this might look a little bit confusing, this is negative x, this is positive x, so this is me going from negative to positive x values, so I will start, my x values will start at negative root y minus z squared and go to positive root y minus z squared. Okay, so now that I've got my x values taken care of, let's deal with the y and the z bounds by drawing the y-z plane. So the projection onto the YZ plane. Now on the YZ plane, this view is a little more simple because I'm kind of looking at this surface, and I can see that I've got this upper bound here that stops abruptly, and I know it stops abruptly at this now vertical line y equals 4. I know this function at the widest point of this elliptic paraboloid lies on the y-axis, and so if I were to write this in 2 dimensions, this curve would look like y equals z squared. So this would be y equals z squared. And I'm sorry, it would go below the y-axis as well. So both of these are y equals z squared. So this would be that region. Okay. Now I can write this again as a type 1 or a type 2 region, and I'm going to go for type 2 because that way I'm going from one function to the other. And so I'll have an equation in the form of y equals something. So this is going to be y equals z squared, and so my y's are going to go from z squared to 4, and my z values are going to go, well, where's this z region? Where does this intersect? To find these intersection points, I can just set y equals 4 equal to z squared, meaning that z is going to be plus or minus 2. So this is 2, this is negative 2, and so my z values are going to go from negative 2 to positive 2. All right, let's set up this integral. So this is going to be the triple integral starting with my constants from negative 2 to 2, with y from z squared to 4, and with my my x values from negative root y minus z squared to root y minus z squared of the square root of x squared plus z squared dx dy dz. And again, we've got the same issue here. We're trying to integrate this with respect to x. We've got an x squared inside of this, so we have the same problem with that integration. So let's try type 3. All right, type 3 is that integral, that triple integral, written in the form of dy dA. So if I look at these y values, well, where does y start? Y starts anywhere along this parabola. Okay, and isn't this parabola just x squared plus z squared? And so my y is just going to start at x squared plus z squared. Any point along this thing, and where does it stop? Well, my y always stops at 4. All right, so these are my y bounds. So now let's look at this xz plane, the projection onto the xz plane. So looking at this along the xz plane, if I'm kind of looking from this angle here, well, if I treat my y as a constant, in this case, the largest projection is going to be y equals 4. So I'm kind of looking at 4 equals x squared plus z squared. Well, isn't this just going to be a circle with a radius of 2? Where this point is 2, this is 2, we've got negative 2 and negative 2. This is 4 equals x squared plus z squared. Now, I could write this as, you know, a type 1 region or a type 2 region, but isn't it much easier to just convert this to polar? Because then I know my r is going to go from 0 to 2, because this is x squared plus z squared equals r squared. And my theta, my angle, well, what's the angle 1 revolution around the circle? That's just going to be 0 to 2 pi. So I can write these, I can write my area in polar coordinates. It's exactly what we did in 2 dimensions. But I'm starting in rectangular coordinates. So, setting this up, this is going to be the integral from 0 to 2 pi, and then from 0 to 2, and then from x squared plus z squared to 4 of the square root of x squared plus z squared dy. And then because these two are in polar, I have r dr d theta. So we're starting in rectangular and then switching to polar. So starting in rectangular, great. I'm integrating with respect to y, not x or z, so that handles this issue I had earlier. And so I know the antiderivative, because this is now just treated as a constant, is just going to be y times the square root of x squared plus z squared. We're going from x squared plus z squared to 4. Plugging in x squared plus z squared and 4, we get that this is going to be the quantity 4 minus x squared plus z squared times root x squared plus z squared. All right, plugging these in. Now I remember that we're kind of doing part of this in rectangular coordinates. So this dy and my y bounds are in rectangular coordinates. These coordinates, so my r bounds and my theta bounds, are in polar. So before moving on to polar, I need to switch these to polar. So my 4 minus the quantity x squared plus z squared times root x squared plus z squared is going to turn into, now generally x is going to be cosine theta, r cosine theta, I'm sorry. Y is going to be r sine theta, but in this case my vertical component is z. So my vertical component is going to be r sine of theta. And so let's rewrite this as 4 minus x squared plus z squared. Well, that's just r squared times the square root of r squared. Well, that's just 4r minus r cubed. So I've just got the double integral from 0 to 2 pi, and then from 0 to 2. Because I have this extra r in here, this is just going to look like r times 4r minus r cubed dr d theta, which is really going to be the integral from 0 to 2 pi, then from 0 to 2 of 4r squared minus r to the 4th power dr d theta. Okay, so evaluating this, we get the integral of 4r squared with respect to r, turns it into 4/3 r cubed minus 1/5 r to the 5th power, going from 0 to 2, is going to give us, well, 2 cubed is 8, so this will be 32/3, minus 2 to the 5th power is 32, so this will be 32/5. 32/3 minus 32/5 is going to be 64/5. Okay? And then we've got the integral from 0 to 2 pi of 64/5 with respect to theta is going to be 64/5 theta, going from 0 to 2 pi, which is just 64/5 times 2 pi, which is 128 pi over 5. And if we did go through the painstaking work of evaluating these integrals using this type 1 and type 2 region, eventually we would get to the same exact thing. So now we want to change the order of integration. So we've got this integral going from 0 to 1 in the x direction, from 0 to x squared in the y direction, and from 0 to y in the z direction. And in this case, we're not given what this function is. We're just told that this function is a function of x, y, and z, and it really doesn't matter because, remember, if we have a triple integral and this is a function that's not just a constant, then we're really talking about 4 dimensions, which we can't picture anyway. But we want to rewrite this as an integral that's integrated first with respect to x, then z, then y. So this integral is going to look something like this. We're going to have this triple integral. It's going to look like dx, dz, dy. So just switching up this order. So let's start by just sketching the integration region. And we know that this integration region is in 3 dimensions: z, y, and x. Now, it's a little bit difficult to picture, but I know that x is going from 0 to 1. I know that y is going from 0 to x squared. And I know that z is going from 0 to y. So let me start with the constant because that's easy enough. I can picture x just going from 0. So x equals 0 to x equals 1. Okay, so I know my graph must be within this region from 0 to 1. All right, I know y must go from 0 to x squared. Well, if I were to draw y equals x squared, so I know this is going to look like that parabola, y equals x squared. Right here. Now, because we know that x must go from 0 to 1, we know we're only talking about this positive portion of that parabola. We know this is eventually going to meet x equals 1. All right. Now, as far as in the z-axis, on the z range here, we're going from 0 to y. So that means that when I'm looking at this thing on the xy plane, so all along this surface, z is equal to 0, right? It's on this xy plane. My z value is going to match my y value. So at this point, well, let's find out where they intersect. Well, x equals 1 intersects when 1 is equal to x squared. So this point is 1, 1, meaning at this point right here, my z value is 1. at this point right here, well, my y value is maybe 1/2, my z would also be 1/2. And so if z is equal to y, then this is just going to be a line with a slope of 1. We can draw that going from here to here. So my surface will look something like this. And for a more accurate graph, we've actually graphed this in Mathematica, where this is the x, this is the y-axis, and this is the z-axis. So you can see that we've kind of sketched this surface here. Now if I want to write this as dx, dz, and dy, that means x is going to be a function of both z and y, so a function of y and z. So I'm going to look at the big picture here and say, okay, how am I going to measure the value of x as a function of y and z? Well, the measurement of x comes from this curve to this curve. My z actually doesn't affect x because I know z is just equal to y, right? My x goes from here to here. And what's this curve in terms of x equals? Well, in terms of x, I know that this curve is y equals x squared. So I can write x as the positive and negative square root of y. Now because I know that this is the positive x-axis, I know that this is really going to be x equals positive square root of y. And so I can say that my x values go from, remember I'm going from negative to positive, I'm moving forward along the x-axis, I'm going from the square root of y to x equals 1. So I've got my x. Now to find out what my bounds would be with z and with y, I'm going to sketch the projection. So let me sketch that projection. Onto the YZ plane. Well, on the YZ plane, I can just picture this being kind of copied and pasted onto this YZ plane, all right? Now, I know my x value is positive. Because my x is just going from 0 to 1, I know my z is going from 0 to y. I know I'm only dealing with positive z and y values here. All right, I also know that when z is 0, y is 0, because z is equal to y. I know this because my z is going from 0 to y. If z equals y, and y has a maximum of 1, because we said that this point occurs at 1, 1, 1, then my graph is going to look something like this, where this is 1 and this is 1. And so this is my integration region on the YZ plane. So this means that when I write z, because I want this dx, dz, dy, x is a function of y and z, I know that z must be a function of y. And I know that y must just be a series of two constants. And so z being that function of y, we want to draw a vertical arrow that's parallel to the z-axis. So it's going to look like z equals something. And what is z? Well, z goes from 0 to y, so z is equal to the region from 0 to y. Y, because it's a series of constants, is just our range of y values, and we know that goes from 0 to 1. Therefore, we have all of our different ranges here. We've got our x, we've got our z, and we've got our y. And so finally, we can write this triple integral. starting with our constants, going from 0 to 1, then to our function of one variable, so from 0 to y, and then our function of two variables, so root y to 1, where this is that mysterious function of x, y, and z. And we know this referred to x, so dx. These bounds referred to z, so dz. And finally, these bounds referred to y, so dy. And this is our integral, and you see how the bounds are just a little bit different than what we started with. Because rewriting our bounds is one of the more difficult parts of this, we're going to have another example. So here we have one more example where we're going to rewrite this as an integral in 6 different ways. So we know that a type 1 solid region needs to be written as dz, dA, these being our boundaries. We know for each of these 3 types we have type 1 and then type 1 and then type 2, and so on for the others. All this really means is that we know this is going to be a dz, but dA can be written as dx dy or dy dx. So let's handle the z portion of this. So we've got y equals x squared. And we can see this on the y-axis that we have this parabola, right? We have this parabola, y equals x squared. As far as our z value goes, we just have this boundary that z is equal to 0. So z is equal to 0. And also that y plus 2z equals 4. So that's going to be this line right here. Y plus 2z equals 4, which is y1. Our y-intercept is 4 and our z-intercept is 2. All right, and this is also bounded by z equals 0. So these are our bounds as far as z goes. And we're not really given, well, the only bound as far as x goes is in terms of y. Or vice versa. Y equals x squared we could write as x is equal to plus or minus root y, so that's this parabola. So we've got all our bounds here. So we've got our x, y, and z. So when we start off this type 1 solid region, we're going to look at this 3-dimensional region to see what our z values are doing. Now because z always starts at 0, we're always going from 0 to any given value. I look at this pink arrow here, this is going to be an equation in the form of z equals something. So our z's, being a function of x and y, are going to go from 0 to, well, what's y plus 2z equals 4? Y plus 2z equals 4 can be written as z is equal to 2 minus 1/2 y, just solving for z. So this line up here is z is equal to, so this is z is 0, and z is equal to 2 minus 1/2 y. So this is going to be our z range. Now for the x and y ranges, we're going to sketch the xy plane. So on the xy plane, if I'm looking at this thing, it's kind of like I'm looking at it from above. If I can picture I'm standing above, kind of where this z is, then I see a parabola that opens toward the positive y-axis. This parabola is going to be y equals x squared. Now I know that I have y plus 2z equals 4. So I'm thinking, where is the y value the largest? Well, the y value is largest when z is 0, right? So over here, meaning that this thing tops off, so it has this upper bound of y equals 4. So this is my y equals x squared, this is my line y equals 4, and that's going to be the same thing. over here. I've got my parabola, I've got y equals 4. Now, if I have this as dx dy, what that means is that x is a function of y, meaning that I'm going to draw a horizontal arrow here with some x as a function of y. Now, at first glance, I might say, well, this is the same function to itself, but I can really break this up if I'm writing it in terms of x, because if I'm defining this as x equals something by taking the square root of both sides, I get x equals positive or negative square root of y. And we can see when x is negative, well, obviously this is going to be negative square root of y. This is going to be positive square root of y when x is positive in the first quadrant. And so our x values are going to go from negative square root of y to positive square root of y. And then our y values are just going to be these constants. Our y ranges from 0 to 4. Not a lot of work there. For dy dx, that means that y is written as a function of x, meaning I will have this vertical arrow here with some y equals. Now I can see my lower bound in this case. As far as y goes, y is always going to be x squared along this curve. And so my y is just going to go from x squared to the upper bound of 4. And where does x go? Well, where are these 2 points? These are just those intersections. I can find that intersection by setting x squared equal to 4, and so x will be positive or negative 2. You don't need to visually solve for something like this if you don't have to, but just to show you where that comes from. So this x goes from negative 2 to positive 2. This is going to give us our 2 different integrals. Either way, we have z going from 0 to 2 minus 1/2 y. So this is going to be our inside integral. For one of these, that's dz dx dy. This will be from 0 to 4, from negative root y to positive root y, and from 0 to 2 minus 1/2 y of this mysterious function f of x, y, z, dz dx dy. Finally, for dy dx, this will go from negative 2 to 2 in the x direction. This will go from x squared to 4 in the y direction. And we're going to have that same z of 0 to 2 minus 1/2 y of our function. And again, that's dz dy dx. So we've got our 2 type 1 regions. All right, on to type 2. So type 2 states that our integral is in the form of dx dA. Let's just write down the important information here. We've got the equations y equals x squared, z equals 0, and y plus 2z equals 4. So because this is dx dA, that means x is going to be a function of y and z. So I'm looking at my x values. My x values are going to start here and end here. Let me draw this so it's more parallel to the x-axis. Kind of start here and then end here. So my x bounds that are going to be in the form of x equals something. So how do I describe this? Well, I know that this is parabolic because I can see this parabola down here on the XY plane as well. Right, so I can also draw this from here to here. Right, so this is just another arrow that I can draw. I can draw as many arrows as I need to see where this function comes from and where it goes to. So my lower and upper bounds as far as x goes. So x is going from, well, how can I describe this? I know that this is parabolic. I know x is just starting from the square root of y. Because behind this y-axis, x is negative, this is going to be x equals negative square root of y. Over here, my x value is positive, so this is going to be x equals positive square root of y. This gives me those x bounds of negative root y to positive root y. All right, now that I have my x bounds, I know I've got two options here. I've got dy dz and dz dy. Either way, I need to start off by drawing my yz plane. So the projection onto the yz plane. If I look at this head on, if I'm just looking at the yz plane, I just have this region as a line here. I know this is my line, y plus 2z equals 4, meaning I have a z-intercept of 2 and a y-intercept of 4. So I've got the same region here, z-intercept of 2, y-intercept of 4, and this line is y plus 2z equals 4. So dy dz means I'm just going to draw an arrow parallel to the y-axis, so a horizontal arrow. My bounds are going to be in the form of y equals something. So my y is going to start at 0, and I can rewrite this in terms of y. Well, by subtracting 2z from both sides, I get y equals 4 minus 2z. This means that my z's in this case are just going to be those constants. So where does z go? Well, z just goes from 0 to 2. For dz dy, I know z must be a function of y, so I'm going to draw an arrow parallel to the z-axis because I know that these function bounds are going to be in the form of z equals something. And so my z will go from 0 to, well, what's this written in up as a function of y? I can isolate this z, I subtract y from both sides, divide by 2, so I get 2 minus 1/2 y. So z is going from 0 to 2 minus 1/2 y, and then y is just going from 0 to 4. So I can write these next two integrals as this one from 0 to 2, from 0 to 4 minus 2z, and then both of my x bounds are going to go from negative root y to root y of this function, and dx, dy, dz. I can write this other type 2 solid region as the integral from 0 to 4, the integral from 0 to 2 minus 1/2 y. And yeah, you might recognize this from the type 1 integral. And again, yes, these are our z bounds in terms of y, and the integral from negative root y to root y of this function. And now this will be dx, dz, dy. All right, just so we get a better understanding, let's run through this one last type of solid region. We've got a type 3 solid region. Type 3 solid region means that we are writing this thing as dy dA. So I want my y bounds to be a function of x and z. So I've got z, y, and x axes. So my question is, how do I get y? So if we look along the y-axis, and it's a little bit hard to see here because now y actually truly is a function of x and z, just meaning that y is influenced by both x and z. Because if I'm looking on the xy plane, well, y starts at this function here. Maybe it's a little bit easier to see down here. Y would start here, and then it would hit y equals 4. If we start up here, then again, we're still bounded by this parabola, but then we're also bounded by this line. And this was the line. Let's just remember that this is y equals x squared, z equals 0, y plus 2z equals 4. Right, so now this is bound y because these lines are parallel to the y-axis, so they're going to be in the form of y equals something. Y starts at x squared and ends at y plus 2z equals 4, which really means y would be equal to 4 minus 2z. Now ultimately y does end at 4, but 4 minus 2z stops at z equals, well, y is 0 at z equals 2. And this kind of gives us that upper bound on this side, right? Because this ends up cutting off at y equals 4. All right, now that I have our y bounds, let's look at dx dz and at dz dx. All right, so we're looking at these coordinate planes, dx dz and dz dx. We're just going to map the projection of this onto this zx plane. So we're kind of looking at it from this angle. From this angle, we see a maximum at z equals 2. And then we see this parabola. So this is our projection onto the zx plane, where this is z and this is x. Now we want to know how to describe this curve. Now we've got x squared, we've got y equals x squared, right? And we've got y plus 2z equals 4. And how can we describe this curve? Well, we know along this curve, both of these equations are equal to each other. Because we're just looking at the xz coordinate plane here, we want y out of the picture. We want to say that this is true for any y value. So we are going to just plug this x squared into this second equation. So we get x squared plus 2z equals 4. And that's exactly what this curve is. This curve is x squared plus 2z equals 4. In other words, we could also write this, and we're going to write this two different ways when we find our x and z bounds actually. So let's start right here. We want dx dz, meaning I'm going to draw an arrow that is parallel to the x-axis, and I know these bounds are going to need to be in the form of x equals something. So my x bounds are going to be functions of z. Now, how can I describe this in terms of x? Well, I can solve this equation for x to get that x is equal to positive or negative root 4 minus 2z. Because this is where x is negative in the second quadrant, this is where x is positive. We're going from negative root 4 minus 2z to positive root 4 minus 2z. As far as my z values go, I'm just going from 0 to 2. When I'm looking at dz dx, that means that z is a function of x. So I'm going to draw an arrow parallel to the z-axis, and this is going to be my z equals. And so I need to rewrite this equation as z equals something. Well, by subtracting x squared from both sides and dividing by 2, I get that z is equal to 2 minus 1/2 x squared. And so anywhere along this region, z is going from 0 to 4 minus 1/2 x squared. That means that my x just goes from wherever these intersections are. By setting z equal to 0, I just get that x equals 4, so these are my intersections. Which means that x is plus or minus 2, and so we have negative 2 and a positive 2 here. And so x is just going to go from negative 2 to positive 2. Finally giving us our last two integrals. All right, so from z, we're going from 0 to 2. X from negative root 4 minus 2z to positive root 4 minus 2z. In both of these triple integrals, our y is going from x squared to 4 minus 2z. And we have our function of x, y, and z, where this is our dy. These are our bounds of x, and these are our bounds of z. Finally, one more. dz dx, so this is going to be dy dz dx, going from negative 2 to 2. From 0 to 4 minus 1/2 x squared. And from x squared to 4 minus 2z of f, x, y, z. So this will be dy dz dx. And there we have it. So we rewrote this in 6 different ways. Again, all of these would yield the same result. So that is it for this section. I know some of these are a little bit difficult to visualize at first, but just keep on practicing and remember to come to student hours if you have any questions.